this is our tutorial number 9, and in this video we are going to discuss about the design of square patch antenna operating at 2.45 GHz. The basic purpose behind the design of square patch antenna is to learn that how we can define variables in CST Studio, and also we will discuss about the importance of defining variables in an antenna design if we are interested in optimization of an antenna. So these are the different three aspects that we will discuss in this tutorial. So this is our simple design of square patch antenna, in which we have different parameters like length, width, width of the feed line, and the gap between the inset feed. So these are the different parameters of an antenna, and these parameters have been defined by using different variables, and these are the different values of these variables. So let's begin. Open your CST and just click on new template, and as you know that you have to select microwave and then antennas, and this is basically patch antenna or planar antenna. So that's why you have to define now the minimum frequency and the maximum frequency. So as we are interested to design an antenna at 2.45 GHz, so that's why we will define it at 2.45 GHz. Okay, so if you have any issue about the basic concepts of simple microstrip patch antennas, then on the link of our previous tutorial have been given in this video, so you can go and just understand the basic principles and the formulas that we have used to calculate the values of length, width, and all the other parameters of simple microstrip patch antenna. So we can design simple microstrip patch antenna in different steps. For example, if we are starting from the design of ground of an antenna, then just go to the modeling and then select simple brick and then press escape key. So for example, we are starting the design from ground. So as you know that we have already defined that the microstrip patch antenna will be represented with the length as a L variable, and its width will be represented with W variable. So for example, if we want to define the width of this antenna along the x-axis, and we have to design that antenna on the origin, so it means that first of all we would like to define half of its width along the negative x-axis and half of its width along the positive x-axis. So that's why value along x-min will be minus W by 2, and along positive x-axis it will be considered as a W by 2. But now this W variable is basically for the defining of substrate, right? For the defining of patch, right? So the value of substrate and ground will be little bit larger as compared to the width of the patch. So that's why, for example, if we want to put the gap of 5 mm here, so it will be minus 5 along negative x-axis and it will be 5 along the positive x-axis. So similarly, if we have to consider the length of this ground or substrate along the y-axis, then we have already defined that we will use the variable L, and half of its length will be along the positive x-axis, and obviously we have to provide the gap of 5 mm along the positive y-axis. And let's assume that we want to define the ground and substrate along the negative y-axis. So along the negative y-axis we will have also minus L by 2, and then we will also define the length of feed line along the negative x-axis as well, right? So similarly, if we discuss about the values of Z min and Z max, for example, we want to start the value from 0, and as you know that the thickness of the copper along with the FR4 substrate is basically 0.035, and its material will be loaded from library, and that would be copper annealed, right? So that will be the material of the ground, right? So I would like to repeat all these values again so that it must be clear. We have considered the value of width along the x-axis, so half of its value along the negative x-axis and half of its value will be considered along positive x-axis. We have provided the gap of 5 mm for ground and substrate because the value of width is basically the width of patch, not the width of substrate and ground, right? And secondly, we are going to consider the value of length along y-axis, and its positive along the positive y-axis it will be L by 2, and along the negative y-axis it will be minus L by 2. And along the negative y-axis we have to define the feed line as well, and the total length along negative y-axis will be L minus L by 2 minus LF. LF is basically the length of feed line, right? And Z min and Z max are basically the values of thickness, and thickness of the copper with FR4 substrate is basically 0.035. So now, as you know that it is square patch antenna, and we have already checked that its length and width values will be considered as a 29, and its length of feed line is 16, and that will be the value of basically value of ground, right? So you can rotate, and you can just check the value of ground. So just press OK. So now all the values will be similar in case of substrate. So just go to the modeling, and then you have to define your substrate and name it as a substrate. So all the values will be similar for substrate as we have already defined in ground. So as we have considered the width along the x-axis, so it will be minus W by 2 minus 5, and similarly its half part will be considered on positive x-axis, and it will be L by 2 plus 5 on Y max, and it will be minus L by 2 minus length of feed line along the negative x-axis. Now you cannot start the substrate from 0 because recently you have started the ground from 0 to 0.035. So as now you have to start the thickness of substrate from 0.035, and you will further add its value of thickness, and value of thickness in case of FR4 substrate is 1.59 or 1.6, right? And its material is basically FR4, right? So FR4 will be selected as its material, right? So all the dimensions of the ground and substrate must be same, right? And you can observe that all the dimensions are same, just we have changed the thickness of the substrate. So now the last step is to define microstrip patch on the front side of this substrate. So as you know that we have to consider the value of width along x-axis, so and the value of length along y-axis, so that will be basically the value of substrate. Now we have to design the simple patch. We are not designing ground or substrate, so that's why there is no need to add some gaps, right, like minus 5 along the x-axis and minus 5 along the y-axis, right? But the Z min value will be 0.035 plus 1.6, which is the start point, and we will further add 0.035 in the value of Z max, which is basically the thickness of copper again, and same copper material will be used, right? So we have to just click on preview. So this is basically the patch of an antenna, right? So moving toward the next step, now we have to cut its central point, right? And central point will be considered as a inset feed cut, right? So it will be inset feed cut, right? So now, as you know that if I show you the design, then this is the total width of feed line and this is the gap, right? So this is our central value. So half of its width of feed line will be considered along the positive x-axis, and its half will be considered along the negative y-axis. And similarly, we have to properly add the gap on both sides, right? So if we want to cut the patch from this portion, then obviously we will define the values as minus WF by 2 and plus WF by 2 along the positive x-axis, and we have also add the gap GPF on both sides. So it will be minus GPF along the negative x-axis, and it will be positive along the positive x-axis, right? And as far as the value of y min and y max is considered, so first of all you have to take the reference point. So you can take the reference point from center, but you have to define this inset feed length as well. So as you know that the upper part is y max and the lower part is y min, and the value at the lower part is minus L by 2. So just take the reference as minus L by 2, right? So it will be minus L by 2, and starting from the bottom point or minus L by 2, you have to just add the value of length of inset feed Fi, right? And as you know that these are the part of patch. So patch is basically starting from 0.035 plus 1.6, and its end value is 0.035 plus 1.6 plus 0.035, right? Now you can define any different material. For example, you can define the nickel and just load it. So obviously we have defined another metal, and that metal cannot be merged in this copper metal, so it will show an option. So first of all, the value of width of feed line is 2.932, and the gap is basically 1, and the value of Fi is 1.2 as per the mentioned values, right? So now here is the value of inset feed, right? So now you have to just click on OK, and as I have already mentioned that when you will take different metal, then this metal cannot be merged, so it will show a dialog box, and in that dialog box we have an option to cut away the highlighted shape, right? So just click on OK, and that portion will be cut it away. So now the last step is to define the feed line. So name it as a feed line, and now as you know that the width of feed line is represented with the variable WF, and half of its width will be located at x min, and its half will be represented at its x max, right? So as we have already taken that we have to pick the bottom side of this simple patch, and that bottom side along the y-axis is minus L by 2, and we have further added Fi as a length of feed line. So that will be the starting point of the feed line, and from this point you have to further add the length of feed line, right? And as you know that its value for Z min will be 0.035 plus 1.6 and Z max value will be 0.035 plus 1.6 plus 0.035. So its material will be copper because we have to define the feed line. So just click on preview and you can observe that it is placed at its correct position. So just click on OK. So these are the different steps in which we can design simple microstrip patch antenna. But now you have to add the patch with its feed line, right? So select the feed line and just press enter. So these are the different design steps in which we can design simple microstrip patch antenna or simple square microstrip patch antenna. So now we have to just rotate it because now it's time to define its feed line and its waveguide port. So now we have to assign a waveguide port at its feed line. So just zoom in the end point of the feed line and now you have to select this surface. So you can use the shortcut key F to select this surface, right? So just select this surface and go to the simulation and go to the waveguide port, right? So as you know that along x-axis basically you have to assign the value of 3 times the width of feed line. So it will be 3 times the width of feed line along the x-axis, along x min as well as along x max. But along the Z min you have to touch the ground for proper propagation. So obviously now we are at the top. If we subtract, as the subtraction sign is already available here in the dialog box, so if I simply write 1.6, it means that we have subtracted 1.6, and if I add plus 0.035, it means that plus minus plus will be equivalent to the minus. So we have further subtracted 0.035 as well. So that's how this feed line can be touched with the ground, right? And along the Z max you must take the 4 times the height of substrate, and you know that height of substrate is 1.6. So these are the different values which can be considered as a standard. So you can just click on preview and you have to just click on OK. So that's all about the design of simple square patch antenna. And in this design we have basically used the variables, and that's how you can use the variable in CST. Now let's move toward the point that what is the importance of the variables in designing different type of antennas. Basically when we have to calculate the length and width and then the width of feed line and all the parameters of an antenna, so from formulas it is very difficult to calculate the exact length and the width. So after the simulation and after checking the results, we have to optimize an antenna. So for that purpose obviously we have to change the length and feed line, length of the feed line and width of the feed line, and similarly length and width of the patch as well. So now if I want to just change the length of feed line, for example, and we have to increase the length of feed line, obviously this feed line will cross the dimensions of substrate and ground. So if I change if I want to change the length of feed line, then obviously I have to go to the dialog box of the ground and substrate as well, because the end point of the feed line and end point of the substrate and ground must be same. So if I want to just change the length of feed line, so I have to change the values in ground, substrate and many other places and in many other dialog boxes as well. So it will be very difficult if I if I didn't define the variables. So now if I want to change the value of any variable that have been shown here in this parametric list, then I can easily change the variable. For example, if I want to change the value of fi and I want to consider it as a 1.5, then I can just easily change the value of fi here, right? So that is the basic purpose of defining variables in antenna design, that we can easily optimize an antenna and we can easily change the variable in CST Studio. And secondly, if I have to optimize the result from the optimizer, then obviously it will require the values of the variable. Either I want to optimize the value of fi or gpf or the length of the feed line or the width of the patch. So these variables can be shown here. So if I want to optimize it through this optimizer, then variables are also mandatory to define in your design. So that's why our main focus was to define the variable, that how we can define the variable and what is the importance of variable. So that's all about the design. So now just go to the simulation and you can just click on start simulation. So this will take some time, and after successful simulation we will discuss about the results of this microstrip patch antenna as well. Okay, so simulations have been completed. Now check the results of S11. So you can observe that it is around about 2.45 gigahertz, but these results needs to be optimized, and you can easily optimize the result by changing the value of different variables manually, or you can use also the optimizer option as well, because now you have already defined all the variables that can be optimized and selected in this window. So similarly you can check its gain as well. So its gain is around about 5.75 dBi, and that is its radiation pattern, right? So that's all about the design and simulation of square patch antenna, which is operating at 2.45 gigahertz. And we have also learned that how we can define different variable and what is the importance of defining variable in an antenna design. So in next tutorial we are going to discuss about the antenna array, and we will design two elements array of the same antenna in our next tutorial. So for our latest videos, please subscribe and press the bell icon button for our latest videos. Thank you.